All right. Thank you so much, Paige, for that introduction. Yeah, I'm Christine. I'm from the Argonne Leadership Computing Facility, and I'm joined by Hannah from the Advanced Photon Source, and she'll be speaking in just a moment. This is the first in a series of webinars and training events, which will focus on ALCF's efforts in supporting integrated research infrastructure. And we'll talk more about what that means. Today, we're going to be focusing on computing on demand. And that's going to be for computing for experiment time analysis, for running experiments such as beamlines at X-ray light sources, but other types of experiments as well. We've done this with other types of facilities, and we'll talk more about that. Um, just to give an overview, today we'll cover an introduction to what we're calling integrated research infrastructure. This is a DOE computing facility-wide effort to better integrate our DOE computing facilities with all kinds of science, including experiments, running experiments. I'll then give an overview of services and tools specifically for on-demand computing, so computing that has like immediate need. So we'll talk about ALCF service accounts and queues. We'll talk about Globus tools for triggering computational work remotely from, your experimental facility. And we'll talk about data management tools and strategies that we offer. Then we're going to hear from Hannah, and she's going to share some exciting work that they've done using all of these tools and capabilities to enable science on many of the beamlines at the APS. And we'll then transition to sort of some conclusions about next steps. So if you want to try out some of these tools or techniques, we'll share with you where to go, where to get help, and then we'll talk about the future of this service-enabled science series. Okay, so DOE has many user facilities. Those on this call may be familiar with the computational user facilities like the ALCF, but it also has 24 experimental user facilities. So these are things like X-ray beamlines like the APS, but also there are tokamak experiments like D3D, and also data aggregation experiments like JGI, where they collect samples of genomes and offer a database as a service. But there's many others in, particle physics, climate science, and more. So many of these experimental user facilities are undergoing upgrades, and we'll hear more from Hannah about the upgrades at the APS. And that often comes along with a large increase in data rates. In addition, many of these facilities are pivoting to make more use of AI tools, and that also changes the complexion of their computing needs. So this combination of upgrades and more AI usage is increasing the data rates and the computing needs for these facilities. So that poses a challenge. So what the DOE has been initiating is a new program called the IRI program. This is a somewhat older slide, but it kind of gives the vision of this program. So essentially, I've just explained like there's this increased need in computing resources for experiments. So this is a gap that we in the computing within the DOE need to fill. Now, we're not at the center of this, however. Like the center of this is not the supercomputer. The center of this are the researchers and their science questions, their workflows, their codes. They've got to get their data, whether it's from an X-ray beamline like the APS or other experimental computing facilities, but also data from maybe other international collaborations and so on. How do they effectively run compute on those data in a way that works for them. And so we at the DOE computing need to think of ways we need to better enable that interface. And so what that involves is enabling, rapid data analysis for steering experiments. It might involve novel workflows using multiple facilities. Say ALCF is on maintenance. Can you just seamlessly send your work to NERSC? That's the kind of things we're thinking about. So at the ALCF, we've thought carefully about these needs, and we've put together a suite of capabilities and tools that we think provide some important functionality in this space. And we're gonna talk about many of them today. The ones we're talking about I've highlighted in blue. So we'll be talking about demand queues, which these are special queues that allow approved projects to get immediate access to computational resources. We'll be talking about service accounts. These are accounts that can be shared by multiple users. We'll be talking about our Eagle file system that enables data sharing in some special ways that I'll touch on. And then we'll be talking about the many ways that Globus tools are enabling this integration. I will say there's other things we're doing in this space, and I'll just mention a few. So one is enabling data portals. So we have something called the ALCF Community Data Cooperative, ACDC, that we've been working with different teams to enable portals where you can share data in a metadata-based way, not just like here's some files on Eagle kind of way. And then also looking in that same vein in sort of dedicated web applications, like if you have a scientific group who has some sort of specific needs about certain computations they need to do routinely, can you just set up a web portal where they can just click some buttons and have it returned to you? So hopefully some of these aspects will be the focus of future webinars in our series. Okay, so let's get started here on some details. So the first place I'm going to start are with demand queues. These are queues that allow fast access to compute resources. And this can be important if you need to do some computation that is time sensitive. So you need to run some compute tasks for a running experiment. You might need it to set up the next experiment in a series if you're at a beamline and you're doing analysis, you're setting up experiments and trying to do analysis on the fly together. Now, if any of you are familiar with using an HPC system, typically compute nodes are not immediately available to you. You usually have to wait in a queue. So these demand queues work in a specific way. They work in coordination with a reciprocal queue called the preemptible queue. So when jobs are submitted to the demand queue, what they will do is they will preempt jobs in the preemptible queue and give those nodes over to the demand queue user immediately. Now, don't feel bad for the preemptible queue users. They know that this is the policy and this is what they have to expect when submitting jobs to the preemptible queue. And we offer on all of our machines, normal queues that are not preempted. So, this is really just a portion of the machines we're discussing here. We offer demand queues on two systems, Polaris, which is a GPU cluster that has NVIDIA A100 GPUs, and Crux, which is a CPU-only machine. And these demand queues have been used by the APS. We'll hear more about that from Hannah, but they've also been used by other experimental facilities like specifically D3D, which is a nuclear fusion experiment, a tokamak experiment that has also used the demand queue on Polaris. How do you get access to the demand queue? We are very selective. We only allow access for teams that have true experiment time compute needs. And so you can email our support if you, after this talk, think this is something that might be of use to your facility. And I will just say, for some specifics, Polaris has a total of 56 nodes available with an aggregate number of GPUs of 224 in the demand queue. And Crux has 64 available nodes with a total number of 8192 CPU cores in that queue. Okay, next I'll switch over to talking about service accounts. Service accounts are accounts that can be shared by multiple users. And this can be very useful for experiments where often the person pushing off the work is really not a person. It's maybe a piece of software connected to an experimental apparatus, right? So the user is the tokamak, it is the X-ray beamline. And the service accounts can be accessed by specified users. So typically that would be people like Hannah or other software developers or people who are in charge of software at these experimental facilities. They do require a security review of the software services you wish to run. However, I will say that Globus Compute, which is a tool for automating job submission, we'll hear about in a second, that has already passed the security review. So if you are interested in getting a service account and running testing some automated workflows and things, if you are able to use Globus Compute, that is a fast track to getting started with a service account. So how do the service accounts work? How do you, as a user with access to a service account, use it? Well, typically what you do is we give you access to some special nodes that are connected to the machine where you can log into the service account, essentially. And these service nodes are where you can do that. So currently we have service accounts available to users on Polaris and on Crux. Okay. Now I've alluded to Globus Compute and Globus Tools, so now I'll talk a little bit more about that. Globus Compute is a tool offered by the Globus service, which most people, their first introduction to Globus is with file transfers, and we'll talk about that. But Globus offers a suite of tools also now in the space of running tasks like Globus Compute tasks, and I'll talk what that means in a minute, but also hosting workflows in the cloud, something called Globus Flows. We'll touch on that as well. So Globus Compute specifically is a tool for triggering jobs at a remote location. So say you have your computer at your experiment. Here is a scientist working away outside of the ALCF compute space. And this scientist wants to send work to Polaris. What they can do is communicate that work to the Globus service. And if this scientist has pre-staged what we call a Globus Compute endpoint, we'll talk about that in a minute. That endpoint process that lives inside the ALCF compute space is also talking to the Globus service. So when the scientist tells Globus, I want to run this task on Polaris, this process running within the Polaris, compute space, which this might be on a login node or on a service node for a service account, it can pull down that work, and it has the ability to communicate with the machine scheduler and submit a job on behalf of the remote user to the scheduler. So this is without the scientist having to log into the machine at all. They can execute a job on the Polaris compute nodes. So this is currently set up entirely by the user, so you do not need ALCS staff to set this up for you. We obviously are here and willing to help you, but this is something you can have control over. And the basic requirements are you need to have a Python environment at your remote site, so where the scientist is sitting, that has the Globus Compute SDK Python package installed. And then you need an environment on the ALCF side, so on Polaris in this case, where you have all the required application software installed. So any, Python packages, compiled executables, containers, etc. One thing to note is Globus Compute sends the work in the form of Python functions. However, that doesn't mean you can't run a compiled executable or a container. It's very simple to write a Python function that can wrap around such an application. And results can be returned either through the function return if they're very lightweight, if they're just a simple string or a small Python object, or you can move files written to disk on Eagle, the file system connected to Polaris, separately with a Globus transfer. And we'll talk about how you can maybe connect those two. So I was a little bit nebulous about what it takes to set up this process that lives inside the ALCF compute space that talks to Globus and receives work from the remote user. This is called a Globus compute endpoint. And this is something that has to be pre-staged by the team on Polaris or Crux in order to enable this kind of workflow. You can create one by simply installing a Python package called Globus Compute Endpoint, which then gives you access to a command line tool, Globus Compute Endpoint. And this will allow you to set up an endpoint process and manage it. Your configuration for your endpoint process will involve information about the PBS job submission and sort of the task resources needed for each compute task you're sending to it. In our recent hands-on ALCF workshop, we had a detailed tutorial on how to set up a Globus Compute endpoint and how to run some simple like hello world type examples. And these slides will be provided later. There's a link here to those materials, and you can try it out for yourself. Okay, so involved in all of this, I was a bit nebulous about like, you just set up the process, but how do you do that securely? And so this is one of the nice things we like about Globus and why we're relying on Globus tools for some of these things is they provide a robust and secure way of doing automation. And specifically for these on-demand workflows, you need the automation to be automatic, right? Your beamline sends some work to Polaris. You cannot have a human in the loop typing in a code or providing some authentication token. You need to have the beamline to establish the connection securely and automatically. So Globus Auth, if you've ever used the Globus website, you're maybe familiar when you log in, you select your institution. Any ALCF user can log in with their ALCF credentials. So you put in your institution and then it will bring you to an authentication page hosted by the facility. So that's fine if you're just a human, but if you're a running experiment, Globus offers some automated authentication tools, specifically in the form of something called a client ID and a client secret. And this is needed for enabling, persistent automated processes that run on a HPC system like ours. So the client secret that you're given, it's a one-time token that's generated by Globus that is responsibility of the user to keep secure. When you provide this client ID and secret to an endpoint process that you're starting up or to any client process that's submitting work to the Globus service, you need to do so in a secured manner. You can create specific policies and rules for the client in secret, which allows you to establish like things about who can use it, etc. And any tools or software that are creating client processes or executor processes, they can access this. Usually what we recommend is you just set some environment variables. And if you have a way that you can set them from a secure file or a GitLab secrets vault or something like that, that's usually a good way of doing it. And I've just included here a little screenshot of what it looks like in the Globus web page, web portal, what you need to do to like set up a client secret. So you create your client, you create what's called an app. So every app can have multiple secrets associated with it. And it's a pretty easy process. It's just sort of point and click. And I will say the secret is not displayed here. So nothing is being made insecure by this slide. Okay, so we've talked a lot about compute and authentication. Often, well, almost always for these experiment time workflows, you need to have some way of getting data to the HPC system. The file system that's mounted on our main IRI machines, Polaris and Crux, is a file system called Eagle. It's a 100 petabyte Lustre parallel file system mounted on several machines within the facility. It, of course, has a facility-maintained Globus collection, which, if you're familiar with Globus transfers, that's sometimes people also call it a transfer endpoint, but I believe Globus is now moving more towards the nomenclature of calling these collections. So we have this facility collection. You can, point and click in the web UI for transferring things. You can also use that facility collection to interact with it programmatically with the Globus's Python package or with its command line tool. On Eagle, we also allow for users, for PIs of projects, to create an additional type of collection that sits on top of the facility maintained collection called a Globus guest collection. So this is kind of like a sub-collection on the main collection that you, the user, control. And I've shown here a little screenshot from the Globus web portal, again, where it shows you if you have access to the Eagle facility maintained collection, you can create your own guest collections on top of that. What that then gives you is an ID number for that collection, just like any facility maintained collection. And you can set it up to point to specific directories on Eagle, and you can give it specific permissions. So you can restrict it to a particular people, or you can open it up to unauthenticated access. So you can actually serve data publicly from Eagle with a Globus guest collection. In addition, you can use the guest collection to, it offers some functionality that's needed to do transfers with the Globus client in secret that we just discussed. So if you want to do automated transfers with automated auth, you will need to set up one of these Globus guest collections on our systems. And we have methods, or Globus offers methods for coordinating compute functions with transfers using something called Globus flows, which I'll talk about now. So this is the last piece of Globus tools I'll be touching upon. Flows is a automated managed workflow system that's hosted by Globus. It's built on top of AWS step functions. If you're not familiar with that type of language, don't worry, we have lots of examples we can show you. And what's important is these workflows are hosted in the cloud by the Globus service. And what that allows you to do is to coordinate actions within this flow that involve different types of Globus collections, or endpoints. And this is, again, a screenshot from the Globus web UI where you see every flow that you submit will have this sort of record that you can look up in the web page. And you can see here, these are steps in a flow where there's different actions taken, and some of them might be transfer steps, some of them might be compute steps, and you can see how they're executed one after another and the time they take. And so all of these different actions are involving different Globus endpoints and collections that the cloud service is talking to on various compute facility machines. I'll say there's other kinds of actions available. There's all kinds. You can do ones for data cleanup if you want to delete files or move files. There are choice actions that will allow you to make sort of branching decisions in this flow, things like that. So again, just to summarize what this looks like is when you run a flow, the remote user will send a description of their workflow, of the Globus flow, to the Globus service, and that's where it will be hosted, and that's where the sort of stepping through the steps will be executed from. As the Globus service goes through these steps, it has encoded within the flow all the different collections and endpoints it needs to use to complete these steps. So when it, for example, gets to this middle step, the transfer step, where it's supposed to transfer input to maybe a machine like Polaris, it knows what the source collection is and the destination collection is. So what it will then do is coordinate maybe a transfer between these two collections sitting on, maybe a file system at the remote facility and onto Eagle. When you get to a compute step, what it will do is communicate with these compute endpoints, which are the orange symbols here. And so it will reach out and tell this endpoint, okay, you need to execute these Globus compute tasks for me. And all of this is tracked in the Globus service, and then you have a nice web UI where you can access the record, the timings, all of the information about all the steps that were completed. And I will say, if you want some more details on running flows at ALCF, we had a webinar last December where I gave some examples of some very simple flows and what does the flow definition look like in the AWS step function language, and how do you pass inputs, and what does that all look like? And so that can be a good resource, and we're also happy to talk with you. Okay, so I've given here now an overview of different kinds of tools and strategies that we're offering here at ALCF to enable experiment time compute tasks. Now we're going to switch gears and we're going to hear from Hannah Parraga from the APS about how they've been making use of all of these tools at the APS and what kind of science that has enabled for them. So with that, I'll transition over to Hannah.
Thank you so much, Christine. I am here coming from the Advanced Photon Source today, hoping to share examples with you about how we're using all of the tools that Christine has described so far, and how our partnerships with the ALCF and also with help from the Globus teams has enabled us to improve our science that we're doing at the Advanced Photon Source. And hopefully these can serve as an inspiration for you or show you how these tools can be put into practice. So hopefully you will be able to get from these examples something that you can take back to your work and apply to help further your own scientific goals. Next slide, please. So the Advanced Photon Source is an X-ray light source. And for those of you who are not familiar, An X-ray light source is an indispensable tool that we can use in the exploration of matter. So this is one of several DOE user facilities, and it's located at Argonne National Laboratory, just a stone's throw away from the ALCF. So we have the privilege of sharing a campus with the ALCF. And in the same manner, we are also a user facility, but our users are researchers who are interested in coming to our facility because they can use X-rays to peer into matter and understand what is going on inside. And this is because X-rays are similar in wavelength. The size is a similar range as that of the size of atoms and biological cells. So we can use these X-rays to look at those atoms and cells and understand them better. And we have many different users that come to the APS every year, thousands of users, and they are coming from all different backgrounds. So some people may be visiting from a university, or they might be coming from a government institution, or they maybe are coming from a private corporation. And the types of matter that they are interested in looking at could be anything. They might be wanting to create better materials for the everyday objects that we have all around us, or maybe they want to study diseases and how we can fight them, to understand biology better, or maybe they're looking at samples from different ecosystems to understand the natural world and what's going on around us. So there are many different applications that people might want to use the Advanced Photon Source to study. So you can see how the science that is enabled at the Advanced Photon Source is really transformational science for our everyday lives. Next slide, please. So some of the transformational science, some examples of what might be researched is that the Advanced Photon Source is being used to improve our energy systems, to make them more efficient, or to make batteries last longer. We are also using it to map the brain, to understand ourselves better, or to combat brain diseases. And it can also be used to create custom materials or to understand existing materials, such as why do concrete bridges fail? How do we make our infrastructure better? Or how do we make manufacturing processes more cheap or energy efficient? And in all of this research, the Advanced Photon Source has actually gotten better. Next slide, please. The Advanced Photon Source was actually recently upgraded. Last year, they replaced the entire electron storage ring and made it so that it produces X-ray beams that are more focused. And this allows us to penetrate deep inside of materials to see what is in the world around us. It's enabled an up to 500 times brighter than the previous resolution of the APS. And this also means having more photons, we can also look at things that are happening more quickly. So processes that are happening within materials, we can image them at less than a billionth of a second. So I know that you coming from the computing world, any of you that are in a computational background are probably looking at this and thinking, well, that means more data. So if we have more photons, we have more data. If we have better instruments, we have better data. And if we have faster data and faster imaging, that means we have to deal with faster data rates. So next slide, please. So this is actually a very large problem in terms of the amount and the rate at which the Advanced Photon Source is producing data. So we have thousands of experiments that are happening over the years. And so far, this has accumulated about 5 petabytes of storage. And that was before the upgrade happened. But over the next decade, we're expecting to generate hundreds of petabytes of raw data for a year. And this will also require compute to process it. It will require tens of petaflops of on-demand computing power to be able to make sense of this data and do something meaningful with it. So that is really where the ALCF steps in and becomes a really critical resource for us at the Advanced Photon Source. Now, all of these numbers here that I'm showing about our data rates and volumes, these are the aggregates of about 72 different beamlines. So this is showing the numbers for the facility as a whole. But I'd like to zoom in now on one specific beamline, which I think really showcases these sort of pushing the boundaries of data generation. And that is the X-ray Photon Correlation Spectroscopy beamline at AID. Next slide, please. So this beamline is one of several feature beamlines that were reconstructed during the APS upgrade. So they were actually torn down and rebuilt, and they have gotten better instruments to conduct their science, which really take advantage of the upgraded storage ring. And this beamline specifically is used to study dynamics. So these are things that are happening with motion over time. So basically, you could look at what would be the effect of changing temperature on a sample, or perhaps you are applying some force to that sample. Or maybe you're introducing something into that sample, like a liquid or a chemical, and you want to see what the effect of that is. So really, we want to see how is this matter changing over time. And there are 2 beamlines here at AID, which allow researching dynamics and matter at different scales for different types of materials. And so there's actually a lot of different applications that this can be used for in performing research on things that affect our everyday lives. Next slide, please. So XPCS experiments have a lot of real-world impact. So some of the research outcomes include studying parts of the body, cartilage and joints, or looking at solar cells, how they can be improved, and flexible electronics, and then different materials like plastic, glass, batteries, different processes in the body, how they're affected by stress. And a lot of different publications, about 255 publications in the past year, have been attributed to the research that was conducted at this beamline. And I want to draw your attention to one specific recent research highlight that came out of this beamline, where they were looking at shear thickening and friction in particle motions as a part of industrial mixing processes. So if you're mixing something, that material might become thicker as you're applying force to it. And this will directly impact the energy consumption that you need as a part of that industrial mixing process. So by understanding shear thickening and the forces from the particle motions, we can help to improve these manufacturing processes and make them more energy efficient. Next slide, please. So this beamline specifically, I've chosen to highlight because it really pushes the limits of data generation. So as you can imagine, if you're trying to understand how things are changing over time, you need to be collecting a lot of information quickly over time. So far in our data management database that we have about at the APS, There are over 450 experiments that have been conducted at the 8ID beamline. And this amounts to about 400 terabytes of storage space used. And this is also stored in millions of different files that we need to keep track of and process. So all of that was mostly collected before the upgrade, but these sorts of volumes are going to increase dramatically as an effect of the upgrade. So one recent experiment collected about 70,000 different data sets, and they each had about 8,000 frames. And these frames were coming very quickly. So it was about 2 seconds for each data set. So this means we need to be launching a job to Polaris and processing a new job on the Polaris supercomputer every 2 seconds. And this amounted to a total data of 61 terabytes. So you can see how if I need to be processing a job every 2 seconds on Polaris, how it's really critical to have tools like these demand queues and service accounts and automated processes and secure and easy authentication methods so that I don't need to log into the Polaris computer and type in by hand to submit a job every 2 seconds because that would just be impossible. And so also these experiments are generating data for several hours nonstop. So they can be going all day long, well into the night, and it's just not something that any human could keep up with trying to process all that data by hand, especially using smaller computing resources like we would have at the Advanced Photon Source, where we don't have our own supercomputers capable of handling all of this data. Next slide, please. So it's really critical to do this kind of data processing because the data that comes off of the detectors that are collecting the photons from the X-ray light source, these are not something that a human can just understand by just looking at the photons alone. They need to be reconstructed using software to create information that is meaningful to the scientists to understand. So here we are using the Boost Core software to do XPCS data processing. So this is basically using the dynamics and creating correlations between them to understand how things are changing over time. So when we are actually running on the Polaris supercomputer, what we're running is this Boost Core package. So before we start any workflow, we go onto the Polaris machine and we set up a compute endpoint, which has the Boost Core package installed into a Conda environment there. And then that will be launched when a job is submitted to those endpoints. Next slide, please. So our partnership with the ALCF and Globus has been really critical for accelerating scientific discovery. So we are able to use this demand queue that Christine described to be able to get these nodes more quickly rather than waiting in the regular production queue that most users would be using at the ALCF. So we're able to spin up the nodes as we need them while we're running this experiment. We also have an ALCF service account for each of our beamlines, and the jobs that we submit will run as these service accounts. And then we have the dedicated computing allocation and project, which is specific for the facility. So we have our own hours that are meant to be used for APS experiments. And we do make use of Globus Compute. So we have a Globus Compute endpoint that is deployed on the Polaris machine. And this is what we submit a job to. So this means that we're able to securely submit to those jobs without having to log in as an individual user and then type in a command to submit to the job queue. So this function as a service platform allows us to execute those jobs remotely on Polaris by setting up that infrastructure and persistent service beforehand. And what does this really mean? The impact for us is that our users do not need to navigate the ALCF world. They don't need to be HPC experts. They don't need to apply for separate computing allocations, which they might not have the resources for. They don't need to spend all of their time during the experiment managing their compute. So, beam time at the APS is a very precious resource. These researchers get to come only for a few days, and the proposal process is very competitive. So, they really want to spend every minute that they have at the APS on researching and looking at their science question. So we want to make the computing aspect of that as easy and seamless for them as possible. And we also want them to have the answers to their questions as quickly as possible so they can pivot and make decisions about their experiment and know what they're looking at while they're looking at it, rather than having to spend weeks or months afterwards processing the data only to find out that they weren't really looking at the thing that they needed to be. So, as you can see, having all of these tools and resources available to us, having the ALCF available to us as a resource is actually really crucial and is very helpful for the users that come to our facility to be able to do their science more quickly and easily. Next slide, please. So what does this look like end to end? So using this XPCS example, what is the life cycle of the data in this pipeline? So we have a software that is actually running the experiment itself, moving the equipment, controlling the detectors, and this is called Blue Sky. And this will trigger the detectors to generate the data to collect whatever it is that they're looking at. And then from there, the Blue Sky software will interface with our data management system that we have at the APS. And this data management system is keeping track about information about the experiment and also where that data lives. So then from there, this data management system has a copy of the Globus client credentials, the secret and the ID. And it will use those along with a Globus compute client to tell where we want to process the data over at our ALCF endpoints. It will then perform a Globus transfer. So we are moving data between a Globus guest collection at the APS over to a guest collection on the Eagle file system at ALCF. And both of these are created, one for each beamline that we have. And we're using those client credentials to perform these actions. And then from there, the compute function will be triggered to run over on the Globus compute endpoint, which is installed under the service account sitting under the Polaris dedicated service nodes. And once that job is received by that compute endpoint, it will then put that task into the queue for the Polaris demand queue, and it will get some nodes. From there, it knows the cond environment and how to invoke the Boost Core software. So the Boost Core software will run on Polaris, and then that will produce some files which have the result of that data processing. And then those files will then be used in a Globus transfer to move them back to the APS file system, where then the scientists can interpret that data and make decisions about their experiment. So as you can see from this full pipeline, the actual data collection is triggering all of the data movement, the storage, the data access permissions, the processing over on Polaris, transferring back. All of that is being triggered and happening without any intervention by the scientists or the users to need to tell it how to do those things. They can just have their results available very quickly to be able to continue on with their experiment and the research that they actually care about. Next slide, please. So beyond the XPCS beamline, we really want to extend this out to all of the beamlines where it will make sense and be an improvement for them. So we do have several other feature beamlines, and we do have other high data producing beamlines, which conduct a variety of different X-ray techniques. But a lot of these use standard common community scientific software, which we can then wrap up in these templated workflows and put them in the same sort of data pipeline so that we can enable science across the facility for many different experiments and many different X-ray techniques happening all at once. So if you are coming from the APS and you're visiting as a user, or perhaps you're one of our beamline scientists, and you are interested in having this method of computation on operation at your beamline, please reach out to me. We would love to help you out and get you set up with this. And next slide, please. So, in summary, the impact of having these tools and this partnership with Globus and the ALCF is really enabling our scientists to streamline their data management and giving them access to HPC resources. And this is going to enhance their ability to conduct research and our ability to accelerate discovery. Next slide, please.
Okay, thank you, Hannah. That was wonderful. A great example and hopefully, yes, an inspiration to folks interested in doing similar things. So, if any of this talk, anything you've heard about in this talk sounds interesting to you, something you would like to try out for your facility, your beamline, your experiment, what have you, we'd love to get you running on our systems. The easiest way to get some time is to request a director's discretionary allocation. All you need to provide is a brief project summary. And I've provided a link here to where to request that. This is a screenshot of the request form. You can request several thousand node hours on either Polaris or Crux or both. And you can also request space on Eagle in the same form. If you'd like to try out a service account or the demand queue, that does require special permission. So please email support@alcf.anl.gov and we will work with you. We're very excited to have people using these queues and service accounts and tools. So please don't be shy. I mean, you can also email me, we're happy to talk to you. I'll say the Globus tools we've described, they are available to any ALCF user. And users of many other facilities. So you could develop a workflow here at ALCF and deploy it at NERSC. We've had users who have done that exact thing. And if you have any special needs that weren't addressed in this talk, if you are interested in doing on-demand computing, but you feel you still have an unmet need here, we're happy to talk to you. Please reach out. And the last thing I'll conclude with is just saying, thank you for your attention. This is the first in what we hope is a series of webinars on service-enabled science at ALCF. We're also expecting to begin a training series, which will be more like hands-on, like we'll get you on the machines and we'll work through some examples together. And we hope to begin that in early 2026. Some future topics for webinars that we hope to explore are, services for multi-facility workflows, data portals. We have an inference service that we've started as well, how to use that. More examples with different applications like Hannah was showing, maybe from other types of domain sciences. And again, yes, the training events that I mentioned. So with that, I'll thank you for your attention again, and we're happy to take any questions. Thank you.
Thank you, Christina and Hannah. There have been a lot of really, really good questions in the chat that have been asked and answered as well. I think maybe time for one question that has not yet been addressed. Zach Anderson asks, does using Globus Compute bypass the need for a security review of the code I'm running? E.g., if I'm using Globus Compute to run my custom analysis code, can I make changes to the analysis code and/or the environment and immediately run the new code? Or do I need to do a security review for analysis code changes?
Okay, that's a great question. So typically, the security review is mainly of the software that is enabling like outside communication. So if your application code is maybe doing reaching out to some server somewhere and pulling down data in a way that's not Globus, then we would need to review changes to that. But if it's just a piece of analysis code that is just running on a compute node and isn't doing any kind of communication outside of the facility, that is fine. Like you can maintain that, modify that however you wish if that's all it is. So it's mainly we want to make sure that things like authentication, account sharing, all of that is being done properly by any type of service application you're running.
Sounds great. Thanks.
Perfect. One final question, and then I think we'll wrap up. Can users or beamline scientists run their machine learning pipelines on Polaris or ALCF for real-time inference?
Absolutely. So Polaris has NVIDIA A100s. We have lots of AI-enabled science running on Polaris. I think I'm trying to think of sort of experiments, real-time experiment computing that's using AI tools. I confess, maybe Hannah knows of some, but absolutely, like we offer machine installations of PyTorch, TensorFlow. We're happy to work with you. You can make use of all of that infrastructure and software on Polaris and on Crux. So absolutely, yes.